Hello all, my name is Binit Kumar Pandit and I am a PhD scholar at IIEST Sipur. I am going to present my paper titled VLSI Architecture of Sigmoid Activation Function for Rapid Prototyping of Machine Learning Applications. This is the outline of my presentation. From this diagram, I will try to explain about the main motivation of this work. In machine learning applications, a huge amount of data is required to be processed in real time, where smarter hardwares and fast algorithms are needed, leading to interaction between hardware and artificial intelligence platform. Different hardware like ASIC, system on chip, graphics processing unit, tensor processing unit, FPGAs are being used. FPGAs are well suited for machine learning prototyping due to its reusability, reconfigurability, and parallel computational capability. Machine learning based computation mainly involves multiply and add operations which can be implemented on any FPGA. Basic components of CNN architecture. A convolutional neural network is made of several neurons which have many inputs x1, x2 to xn and a constant input bias bk. The data inputs are multiplied by weights and added to the bias. The weighted sum is given to activation function block like that of sigmoid activation, which can either fire the neuron if input is greater than certain threshold. Several neurons combine to form a feed-forward network having input layer, hidden layers, and output layer. Several stages of convolution and pooling layers combine to form a complete convolutional neural network architecture. Sigmoid activation function is a nonlinear activation function, and polynomial approximation is a viable solution for the hardware realization. In this slide, I will explain the algorithm for the Chebyshev's polynomial approximation. The Chebyshev's polynomial approximation provides a shorter number of iterations or product terms. The algorithm takes ck and tk as inputs and gives approximated expansion of given function. Ck is the Chebyshev's coefficients and tk is Chebyshev's polynomial. The algorithm goes like this. First, the number of Chebyshev's coefficients required for W bit precision is decided. Then the given function f of x, here sigmoid activation function, is written in Chebyshev's series expansion using the recurrence formula given as the following. Then the Chebyshev's coefficients are calculated by using numerical integration methods or any other integration method, but in our case we have used trapezoidal integration function for calculation of Chebyshev's coefficients. Then the calculated coefficients from the step 3 is put in the step 2 to get the approximated expansion. We have neglected any values that is too small, like of the order of 10 power minus 12 or of the order of 10 power minus 15. The Chebyshev's polynomial is given by this formula for range minus 1 to 1. For different k values from 0 to k, the Chebyshev's polynomial is calculated like this. The Chebyshev's polynomial expansion of sigmoid function can be derived by using the formula. Then different bit precision of 16 and 8 bit polynomial expansion of Chebyshev's is been calculated. Then we have compared the sigmoid mathematical function versus Chebyshev's approximation output. From this graph, we can conclude that the both Sigmoid mathematical and Chebyshev's approximation are almost same. This table shows the output values calculated by using approximation output in the hardware and in the software platform for different number of bits in the hardware 8-bit and 16 bits for the input range -1 to 1. The output tabulated in previous slide can be verified from the simulation waveform given for 8-bit and 16-bit. Post-implementation relative error can be observed from the table, and we can see as the bits are increased, the error gets decreased from the two graphs given on the right side of this slide. And we can see that the graph in the red decreases the error and gets smoother after the input values of 0.25 to 0.50. And the table shows the relative error for hardware obtained values and mathematical values. This is the RTL schematic generated by the Xilinx Vivado software. Post-implementation resource utilization, time delay and power consumption on Xilinx UltraScale plus MPSoC ZCU104 is given in this slide. We have different tables for resource utilization, power utilized for different bits, and number of bits for time delay. Here we can see the different resources used and available resources on the given Xilinx FPGA board. Conclusion and future plans. The proposed work shows the VLSI architecture implementation of the sigmoid activation function, optimal calculation accuracy with faster operations taking the advantage of fewer iterations and product terms provided by the Chebyshev's polynomial approximations is obtained. The proposed VLSI implementation has been tested and comparatively verified with some most recent and notable existing works, and it proved to be suitably accepted. The future direction of this research has already been focused on applying the presented method in an end-to-end machine learning application of sign language recognition with an expectation of having exciting accuracy leading to the deployment. These are the few references used in this presentation. Thank you.